All right, I think this is as good as it gets in terms of people, so let's get started. Good afternoon. Sounds a little odd. Good afternoon. Normally it's good morning, but we have to change the time of the seminar because this is the only time it can happen with all the classes and stuff. Thank you for coming. Good afternoon, everybody. Our speaker today is Syed Khalil. Syed is a geologist with the Coastal Protection and Restoration Authority of Louisiana. Syed's expertise is in the transport and dynamics of coastal sediment, particularly in regards to coastal restoration and protection. And you can imagine how important that topic is in Louisiana, right? They're losing a lot of ground in Louisiana every single day. They say, what is that, like a football field every minute? Or something, yeah, in 1 hour, yeah, something like that. So anyway, so in that capacity, Syed is an advisor to the Executive Director of the Governor's Office of Coastal Protection and Restoration in Louisiana. So I guess he has some torque in terms of the real actions that are implemented in the field. And I think this issue about sediment transport and how it can inform coastal restoration is very important to all of us. And that's the main reason why I thought that it would be good to have him come and tell us about all these lessons learned and how we can, put it to work. Prior to his position, Syed was the director of the Geological Survey of India. He was also a United Nations Fellow at the University of Hawaii. And he has been all over the world, Pacific, Mid-Atlantic, Indian Ocean, Arabian, Mediterranean, Japan, and South China Seas. So a lot of experience to tell us about. Anyway, thank you for coming. And
thanks, Jus. I'm honored to be here this afternoon, ladies and gentlemen. And it was long coming. I mean, if I would have come in the first invitation from Jus, it would have been 2-3 years younger than what I am now. So that matters nowadays when you are at my age. But anyway, that is very nice, and I really appreciate this invitation. And also, I'm just petrified by the beauty of this place. It's beautiful. The coast is nothing new to me all of my life. I have been on the different coast. But this is a good, very pleasant place and to be, and I'm sure I will be returning back soon, especially with my grandkids. So they will love it. Anyway, coming back to my topic, I chose it because you guys have river, you guys have bays, you have problems, but of course the magnitude difference and intensity is different from what we have in Louisiana. And the reason for that is simple, that there are 3 things which I like to mention here. We have the river, and the river was actually, we changed its role. And when you, I shouldn't say mess up, when you play with the nature, there are some give and take. So that's what happened with Louisiana, with flood control. We changed the role of the river, and then we have ecosystem, and I will talk about that a little. So, as Jus has said, that I have been world over going through this. A lot I have seen in my life, but never have seen such a heavy engineering of a fluvial system in any part of the world. And that has resulted into certain disasters. Definitely, it has some consequences. And that consequences is also what I call eco-catastrophe. There are other factors too, but this is a major factor of engineering of the river, and where you choke the sediment, which I will talk about that, and also this unprecedented effort that we are making, to mitigate and to correct the situation is also unparalleled. We're talking about billions, billions with B, that $50 billion worth of master plan with him. Plan is always good, and that's why we have planned for ecosystem restoration. First off, let me tell you this, that we have a general idea of ecosystem restoration when we see, but for convenience sake, what I do normally is I parse it out in 2 different restorations. Sedimentological restoration and ecological restoration. What sedimentological restoration does is that it gives you the geomorphic forms. And the veneer is that ecological restoration becomes there. And I always give this example of iceberg. What you see is a tip of iceberg, and that's why we always get confused. I mean, it's human nature to perceive what he sees. So we always get confused with not confused, I should say the word, but we should always get more emphasis to the upper veneer. But we lose sight of the 9/10 of the iceberg, which is below, which is the sedimentological substrate. And that's where this Louisiana Sediment Management Plan comes in the strategy for restoration of a degrading ecosystem, which is Mississippi River Delta Plain. So what I'm going to talk in next 40-45 minutes is I can only give a glimpse of these topics because they are, as you can understand, they are a topic in itself, one talk in itself. Major deltas of the world, engineering and management of lower Mississippi River, wetland loss of the delta plain and its causes, importance of wetlands, America's wetland, that is ecosystem of coastal Louisiana, strategies and plans to mitigate this degradation. And this is what I like to tell you, ladies and gentlemen, and I have a master plan there. That's very important to plan, and that's what I will try to emphasize later too. And then this plan has to be supported by a very robust sediment management strategies, and where this comes in. So major deltas of the world, this is common. You might have seen this a number of times, but just I'm sorry for this repetition, but just to set the stage, we have 33 major deltas as was Jim Strisky of Colorado, School of Colorado, University of Colorado. And he says, as he rightly says, that 24 of these major deltas are, and of 33 deltas, they are sinking, and mostly because of human intervention. This is a good thing which has been mapped, which is developed by Erickson and others. And it says how we differentiate and how it affects the human being, our population. So that is how he has classified the extreme is where these deltas, and that time it is talking of 2006, by that sea level rise trends of 2050, right, that time now it must be changed a little bit. So he has classified 3 deltas, Nile Delta and Ganges Brahmaputra, where I come from, India, that I worked on that delta. And then you have the Mekong Delta. And these are the major deltas which will affect really more population. They're heavily populated area, believe me, it is much more. For example, India population is 4 times that of United States, and the area is 4 times less than us. So you can imagine the population density. So that is how it is. And then high is 1 million to 50,000 and medium is 50, just to give you a perspective of what we are. So Mississippi comes under high vulnerability in the whole scheme of the things. And just to set the stage again for the role of the river, the Mississippi River, you see this how we have delta ties by dominant processes. The fluvial process is dominant in Mississippi River, which is in, if you see that, it is here in the top, and then you have this delta is tide dominated and wave dominated, but ours is here. And that's what I wanted to emphasize, the role of the river in this delta processes. So management and engineering of the lower Mississippi. This is what happened is I will talk to you, this role of the river as such. Any fluvial system is mainly used to be right from the dawn of civilization, is the navigation and commerce and resource utilization. That is very common utilization of a river. But what happened in 1927, the great flood of 1927, which is a great devastation, and it inundated almost 250,000 square miles, and 500 dead and home destroyed and displaced by 700,000 more. The point I want to make is that time the losses were 1 billion, and with time the federal budget was hardly 3 billion. So you can imagine the devastation, and naturally what people will do whatever it takes to correct the situation, and that's what's done. This was done actually that Flood Control Act of 1928 was authorized that time, and the nation's first comprehensive flood control and navigation act was enacted that time. And this is the largest flood control project in the world with levees. I mean, the lower Mississippi River is about 1,000 miles long, and floodways and channel improvement and tributary basin and all these things that happen. This is what happened with this. So if you look on the left side of the panel, you will find this is meandering distributary, which is the FISC map of 1947. FISC have mapped that river historic courses, and as you know, when old stage of a fluvial system, it start meandering, and that's what exactly it was. But then, because of controlling that levee and what has been done, this is a 1958 river flood capacity diagram, which was developed, and this capacity was developed on model of by considering three range event. One was in 1930 January and 38 February, like that, and 1950, something like that. It was the three rain events were there, and that's how you see it put the river in a kind of straight jacket. And if you see this, this is what is no more natural fluvial system. It starts from the top. If you look at that, is old river control structure. What we does, it changes. You know, the river always follows the hydraulically efficient pattern, so to the sea. So this would have been much easier shot and go sweet to this. But we intentionally created this. So what we did, we created this old control river structure, and that diverted 70% through Mississippi River and 30% through Atchafalaya. So these are the two. And if you look at all these things, we have Morganza floodway for that release the water in high water. We had this Wanikeri spillway to release the water in Lake Pontchartrain. Like that, we have the spillways, floodway, drainage structure, locks, and all sorts of engineering we did on this. And also, if you see that, I will talk in a minute, we have these diversions, freshwater diversions here in Davis Pond and Carnarvon. This is Davis Pond here, and it should be Carnarvon should be here. So this is how we have all these structures and engineering of the river. So no more natural fluvial. So that has resulted into, there is some article I saw in 1930 National Geographic in late 19-something that if we have this, this will be consequentially bad for the posterity. But I know how many people knew that they will be, by putting it levees, what are the consequences would be. So let's see this, what consequences. So basically now we have more than 38,000 dams on the Mississippi River and tributaries all through. Then we have 1,000 miles of levees around, continuous levee. We have meandering cutoffs. We have bank revetment. We have soil erosion control. And this has resulted into reduction in sediment supply from 400 million metric ton in 1900 to almost 1/3 in 145 million metric tons per year from 1987 to 2006. This is a work of Mead and others. So they have calculated this much. Suddenly you are choking the supply of the sediment down. And on the top of that, what we did. If you see these four panels, these are so this is the historic distribution of the flood production levee. I mean, this is what the historic used to be. The distribution used to be all this going to the wetlands. The sediment and water used to go to the wetland. And then this type of lobes, delta lobes, were built over the period of 6,000 years, which formed the Mississippi River Delta. So what happens that this process is called avulsion or delta switching. So as I said early on, the river always follows the hydraulically efficient path, and that's what is done. It came here first, Sepremont, and then it moved to this, then come again. Like that, it keeps switching, and presently we are here at the Belize or the Burstford Delta. So this took about 6,000 to 7,000 years. And then in 30s, when we choked all this, it restricted the flow along this. So this was stopped, this place. And that resulted into this such a situation. The red you see is all the wetland loss. And predict the historical and projected land loss. So what it is, if you look at these two panels in 1922, the delta plain was 25% bigger than what it is today. And then this is, so now you do the math, in 6,000 to 7,000 years we create this, and within 100 years we lose almost 25%. And if we continue in this path without doing anything, we are again going to lose more than 22,000 square miles of land. That's the situation at this moment. And this, just to make sure that we understand this loss is not same across the board. They are different because of the geological setting, again the point I want to bring. So this is the delta plain where the loss is related, as you can see here, with the time series. It is time loss. So land loss is related to the time as it goes, very related time. And so if you see this area, the recent lobes area of this terrebonne, they are really losing fast. If you come to the other place where it is made or marginal delta environment, deltaic environment, you have normally a moderate gain in that area, and it is because of these two places, this Wax Lake Delta and Atchafalaya Delta, where they are accreting. So these are the two delta where their accretion of sediment is there. And if you look at the Chenier Plain, there is absolutely no relationship, and it is most of the loss is due to the storm events driven. That's on the. So what we see across the board is we have this land loss as calculated by USGS of 12 to 16 square miles per year. Recently, they have come up with some reduction in the loss to 10 square miles a year. So this is where we stand in that. So what is happening? It is land loss and is a sediment starved system basically. The levees has on one hand, all these dams have choked the river sediment supply down the line, and the levees down has choked it further. It has prevented the sediment input in the marshes. And then on the top of that, what is happening, we are losing, I mean, it depends on whom you're talking. Oh, I went too fast. Yes. So we are losing somewhere around 125 million cubic yard per year out to the ocean. So this is what we like to tap that. So at one hand, it is not going inside the wetland where it should go. On the other hand, we are losing. So this is a very tricky situation that we need to capture this load, sediment load which is going there. So other causes of land loss in addition to dams and levees are the canal dredging, which you see this here. You see the canal which has been dredged here in California Canal, in Trinity, Barry Islands. Similarly, other canals have been dug here. Here is your levees. So these are the anthropogenic causes, the human-related causes, which is almost caused 70% of this loss. And 30% is natural causes by storms, hurricane, relative sea level rise, eustatic and subsidence, consolidation, compaction, and all this. What I want to point it here is this, how you see this Florida, Alabama, and I saw this map there in your aquarium. So you see how red it is, and this is subsidence. Another talk that we are trying to get handle, and we have just started doing the direct measurement of subsidence. So this is, and then if you look at that, also we are relative sea level rise is the maximum highest in the Gulf Coast. We are there. So we are actually losing faster than any other place. So what is the summary of the land loss? Historical sediment loss no longer delivered to the natural conditions along the deltaic plain. Natural land loss continues, erosion, storms, and all that. Human-related influence increases the land loss, and so is the 70 to 30% loss, anthropogenic as well as the natural causes. So what is the importance? Why we should worry about this? So we have here, first is definitely human. Humans are very important, and that's 2 million population is a risk. That's number one. And then all these marshes and all this wetland, they protect to the all the industry related to oil and gas and ports and fisheries. You see, energy is $70 billion a year, ports $35 billion a year, and with all these jobs, and the fisheries are $3 million a year, and all the total job is about 2 million, and so is the tax generated 7 billion. So all these things are there. And if you look at that, the significance of coastal Louisiana, and I will come back to this place, this thing, if just you shut down this Port Fushon, and I will come back to what we have done for this, you will get GDP goes by $8 billion. So this is something mind-boggling. And you have 18% of the world supply here. You have the vessels going here. You have the grain supply. You have this cargo, and then your fisheries. And then top of that is what you have is here. What is the asset value of the Mississippi Delta itself? I mean, you can debate about this value, but then this is something between 237 billion to 4.7 trillion and all this stuff. So that this is worthless. So not worthless, priceless, right? So that is what it is. So what is at stake? Lots of things in line. If we don't do anything, and as such, doing nothing is not an option for us. If we don't do anything, we lose. The trajectory is that we are going to lose some more than 2,000 square miles. We already lost 1,900 or 2,000 square miles in the 80 years, and then we are going to lose faster because of the high rate of subsidence and eustatic sea level rise. So where we stand now, I mean, our homes will be gone, naturally the jobs will be gone, and then our culture will be gone. So lots and lots of things on the line. I mean, naturally, as we all know, that if your coastal ecosystem is weak, then hurricanes affect more. We are more vulnerable to hurricanes, and that's, I hope the Irma doesn't hit that much in Florida, and that's what we are at this moment. So what are the strategies and plans? So there comes the plan, and we need to have the plan. That's what I say. The plans are important, and I will show you how plans we were doing for a long time, and then it was time to implement it. Unfortunately, all these things came, the impetus to implement this plan came after certain disaster. That's the unfortunate part, that we reacted to these disasters, but at least we are there. There are three things which is really the turning point. The flood of 1927, Katrina and Rita of 2005, and deep water horizon in 2010. And I'll show you what has happened with that. So we had this plan after just for a reference, I have given you the 1930s, we have this Flood Control Act of 1928. But the first indication that we realize in Louisiana that we are losing land is in 60s. That was the first perceptible land loss. We started feeling the land loss in 60s. So it happened in 30s somewhere, we started having the levees, but we felt that in 60, 30 years later. And there, when we have this Water Resources Development Act of 65, and they have a coastal zone management program and all these things happen. But the first real concrete step was taken under Coastal Wetland Planning and Protection Restoration Act, or BRO Act, or CUPRA we call it, in 90s. And that gave us some $20 to $30 million to do the restoration projects. And we were doing the restoration, we're not talking the protection, we're doing the restoration. And looking at those money, and it looks like pittance, but that time it was quite a big money. So that is what it is. And then, till 2005, we were just doing restoration. I still remember as a part of it, I'm part of this since 2000. So we were doing restoration and was thinking about how restore. Came Katrina and Rita, and where we have in 2005 the Act 8, which actually triggered the plan. And you see, we had all the plan all along. And also in the plan, if you look closely, if you look on the top, all this plan Coast 2050 and all this stuff we have, this plan, there is a common theme there, sediment. We need to drive sediment, put the sediment in place. And so the people never perceived and never called it out as such as a sedimentological restoration. But everybody knew that it has to be sediment. But the problem here is that we thought that we have sediment all over the place and we can do it. So we have never paid an attention to the sediment and sedimentological restoration the way it should be, till we started having that. So anyway, so this is, then we have Deepwater Horizon in 2010, and this gets, it has some, it really woke us up that how important a robust ecosystem should be to prevent that kind of injury to the system. That's what when we realized. And then also it brings some brighter light that it brought some funding through penalties of the, so criminal and civil. And then we developed the 2012 master plan, then 2017 master plan, which I will talk. And that, as I said, that is important to have a plan so that we understand, we keep coming back to the issues, that where is the problem, where is the solution. So that's what we have been doing. So I talked about Hurricane Katrina. We all know about this, that it was 2,000 people died and displaced, and the economic loss was somewhere 108 billion, and some people say it's up to 250 billion and all. So looking at Harvey, it is much less, but hopefully Irma doesn't do that harm. But anyway, coming back to the act which was passed as the Louisiana legislature after the 2005. So it has four things it did, important thing it did. It has an integrated, it asked for an integrated team effort to jointly coordinate the master plan development with federal agencies and political subdivisions and levee districts. So what we did, we're talking about the protection and restoration. We were not talking only of restoration. Then we addressed hurricane protection and coastal restoration effort, both short-term and the long-term. And then we incorporated structural management, that how we have the building code and all this management. And Coastal Protection and Restoration Authority, CPRA, was formed that time. And we were in DNR, that is part of Department of Natural Resources. We were taking restoration out, and we brought some people, engineers were brought from the DOTD, that is Public Works Department, and we merged together and we formed this entity to take care of that. We realized that we have to merge these two. So we developed a sustainable plan. How we have the restoration measures, that ecosystem restoration, protection measures, levees and floodgates, and the non-structural measure is the elevated homes, businesses, improved building codes and all this stuff. So, but the challenge was, how do we integrate all these three together so that we have the best of the benefit? So we developed the Coastal Master Plan. What is this Coastal Master Plan? Now we have advances. This master plan advances a comprehensive and integrated approach to protection and restoration. That's what I am telling. It is based on best available science and engineering, incorporate extensive public input and review. We had talk to the public and how they feel, what they feel about it, and then identifies investment, and that will pay off not only for us, but for the posterity. And it is required by law to update it every 5 years. But there were certain challenges to this. This was the, the managing of a coastal environment is very complex. It's not straightforward that you do this, you get this. No. And if you try to model it, numerical model can go only this far. And to really replicate is only way you learn, which we are now incorporating, is adaptive management. Because there is no boilerplate template for restoration. You can't go and say, okay, this is Barrier Island, I'll put this much and this is done. It's not that simple and easy. Or you have choked the sediment from the river, now let's poke holes in the river and you're done. No. Once you have done it, difficult to undone it, and it takes time. And so this complexity you have to comprehend. And this complexity, to overcome that, you have to do some sort of going back and forth, the adaptive management as we call it. So that is a challenge, complex. Then that we have the planning horizon, we are planning for 50 years. What will the trajectory of sea level rise? What is the condition of subsidence? What hurricanes we will put in? I mean, all these uncertainties are there. So then you have the multiple project types. And then you have the diverse community need. The people say that, okay, you open the diversion, my fishes are gone, my shrimps are gone, my oyster is gone. So these are the things you're talking about, and that is really, and what options we have? The options we have is the risk reduction versus restoration. We reduce the risk or the restoration, how it complement each other, that's a challenge for us. And the near term versus the long term, the benefit. Sustainability and the different stakeholders' preferences are there, and that's what a challenge passed for the Coastal Master Plan team. It's very challenging for us. So Coastal Master Plan objective similarly is flood protection, try to have the natural processing, calculate the whole, build the land, and which will have the coastal habitats and which will save our cultural heritage and will become a working coast. That's our objective. So the main driver is reducing flood risk. That is the main. People like to reduce the, or building mill. So you have two things. To protect the land or reduce the flood risk by levees, and you have to build the land for the restoration. And both of these, you have the sediment. The theme, the thread which runs through this is sediment again. So I'm time and again just trying to understand that this is the thing which we need to understand, that sediment is crucial for all these things. So this is, we said 2007, we had a master plan. We started with protection features and restoration features. I'm not going in details of that, but just to tell you that these are the features we started to look into that. And then came the oil spill, which really, as I said early on, that in 2010, and 11 people died, 17 injured. And then the oil spill happened with millions of barrels in the Gulf of Mexico, and we were really affected because the whole system is so fragile. The whole system is fragile. That's the main thing, that when you're weak, the enemy attack you more. So this is what happened, and then that followed by 2012 comprehensive master plan. And this was really one time, and this was really a very important step. 2007 was the initial stage, but then we really have our act together. We developed a very good scientific basis of this, and we developed the strategies. If you look in the bottom, these are the strategies, the structural protection, that is levees, bank stabilization, oyster reefs, ridge restoration, shoreline protection, barrier island restoration, marsh creation, sediment diversion. All these things, if you look at these are the levees here. We plan, then this is the Barrier Island system here in the southeast Louisiana and the Chandelier Islands. And these greens are the marsh creation we projected, and we planned for these marsh creations. And these are the diversions, area of influence or diversions. These are the, so this is how we plan in 2012 to integrate what is the long-term and short-term plan we have for. And this is just to give you an idea of the funding sources. If you look at the funding sources, we had some permanent sources like state mineral revenues and Via Gomesa, but what came from the after Deepwater Horizon is Restore, NIFWIV, NERDA. So this is what we call, and we have in our kitty some $10 billion for this for the next 15 years. But we need more, like our plan is for 50 billion, so I'll show you in a minute. So what we have done since 2007, we have secured some 20 billion, as I said, within the parishes. We are calculating what parishes also have got for protection and restoration. We moved about 120 million cubic yard of the sediment, and then we created or benefited some 36,000 acres of land, and then 282 miles of levee improvement, 60 miles of barrier islands we built and restored. So why 27? 2017 master plan, again 2007, 2012, 2017, because we have to, by legislation, every 5 years we have to look into that. At times it looks odd, why every 5 years, but then it is good that it keeps reminding of what we have done so far and where we are going. And that's what the way is to go. Any restoration program should be like that. There should be have a plan and we follow the plan. And that's what it is. So this is required by the law, but then you improve the science every day, you get the improvement in science and incorporate new ideas and information. And adaptive management is one of that we have incorporated very heavily in this master plan, that we will do that. And the flood, focus on flood risk and reduction and resilience, and emphasis on the communities in this plan. So again, this is the different, again in this plan we have this, all this, say flood risk and non-structural also we have incorporated by having building code. We have levees, barrier islands, shoreline production, bank stabilization, marsh restoration, and barrier reef, hydraulic restoration, and sediment diversions. These are the main, we have been in the 2017 master plan. So what it does, it will have, now it is on, and just March we released that and we accepted. 124 projects we have planned for that, and this will reduce the flood damage by $150 billion, and it will create a land of some 800 square miles of land will be created by this. This is our plan that it will happen. You see all these area influence that will come from the sediment diversions, and you have this, these areas are this non-structured risk reduction. Then you have the levees, you can see the levees here all around, then barrier islands. And these are the things that we are trying to do in 2017 master plan. So funding, if you look at the funding, it is very, so we have for restoration, we have funding of 50 billion, and that is 25 billion for restoration and 25 billion for risk reduction. And in sea, this marsh creation is almost 18 billion, and sediment diversion is 5, and others are less. Similarly, here we have the levees, it's 19 billion, and this is for non-structural, that is the building code and others. So what we are trying to do is create land as much as possible. That's where it boils down to, and I will talk in a minute. What happens in a marsh creation, you create land much swifter than diversions. And so the marsh creation of barrier island, we have done a lot of barrier island restoration, almost all of them during 2012 master plan. So this is dredging projects we have done, and what I want to show you here is this. We are trying to use the sediment from the river, which is renewable sources, and I will talk about this in a minute. So this is the barrier island projects. I just saw the Dauphin Island also here, and this is where in the morning when I went with Juice and saw the barrier islands here we have. What we did, this barrier island Louisiana, they have a unique feature. They are in the Gulf side is the sandy, and this is the back barrier marshes. We create the marsh here by dredging here. So this is how we try to replicate the geomorphic form and ecological function. That is the whole thing that we try to do. First you set up the form, and then geomorphic form, and then follow the ecological function will follow with vegetation, and that's the main thing we are referencing to, and I hope that's what you guys will be doing here. So I was talking about the Port Fourchon. If you shut it down for 90 days, this is what happens. We lose about $8 billion of GDP. This is Caminada. We built, this is 13 miles long headland. And this is the refinery. And this is the Port Fourchon here. So this was built recently, just completed. It is $215 million project. We brought the sediment from 30 miles from ship shoal, and we hauled about 15 million cubic yards of sediment to put it. So you can see this is what we have done, and this is how we're trying to save our port and your oil facility. So then the second thing is marsh creation, second major, I mean three major strategies I'm talking out here is burial and marsh creation, diversion. So this is the marsh creation where we can dredge the sediment, bring it. So this is the first time we dredge, we nearly dredge from the near sources and put it in the marsh creation. But there, what we did, we brought from the river 4 miles through the pipe and put it on there, and BioDuPont was built. What happened that we thought, whoa, this is a as how much sediment is coming and all that stuff, but this is how it happens, that it is slow. But once it's started, you have established the natural process, it will go on. So the thing is that you have to kick-start the thing. So what we thought that, okay, we need both the things. We need a longer-term solution by this diversion, and then also we need the shorter term by using dedicated dredging marsh creation. So what we are trying to do, the best we are trying to do the measuring sediment management is by having the marsh creation simultaneous with the sediment diversion. That's what we are trying to do. So, oh man, it's not moving. We did something or what? Huh?
Escape. There you go.
Okay.
Try to go back in, see if it's working.
Okay. Thanks.
Sure. Well,
So these are these various sediment diversions which are proposed in the 2012 master plan. This is what we are trying to do, is a mid-Belt area and mid-Britain sediment diversions, and this is what we have this in access to the sediment here and the bar, and this is the proximity. So these are the two. We are at this moment we are consulting here, but we are designing this. This is the engineering and design. It takes time for EIS and other things to be done. And then this is the conceptual design, how diversion will work. In the channel, you have the gate, you have sediment diversion structure, outlet channel, and this is how diversion channel will be here. So the peak flow is 75,000 CFS and base flow is 5,000 CFS. And this is the land building over 50 years. We expect that it will build 38 square miles or 100 square miles in the next 50 years. So this is just a model based inside land change in outfall area, if you see that. And if you look at that, either year 0 and year 6, the red is the land you're building. And then if you look at these two diagrams, you can see within 10 years what difference you will make. All the red are here, which are the land. So this is how we expect and we model and we are predicting that the land will be built. So this is the recommendation of the sediment recommendation. What will diversion do in the land loss is that in this area, in the vicinity of that, it will reduce the land loss by 50 to 65%, and the other side of the river, it will reduce to 35–40%, where the outer perimeter, it will reduce to 20%, and outer perimeter this side of the river, east side of the river, 15 to 18%. So this is how we envisage that it will change the scenario and the land loss. So coming to the sediment management strategies, what are those? So land loss is what is. When we talk of the land loss, we normally talk of the square miles of the area, in the surface area. But what has happened actually is that we have this land loss and we lose sight of the void it creates. We call it accommodation space. Modern of USGS has done in that, and he calculated about 4 billion cubic yard of accommodation space will be created by the land loss. And then if you think that, then what we did, we calculated the sediment which needed to fill that gap, the historical loss. And naturally, it will be not the same volume, but it will be more because of the sediment characteristic and cut-to-fill ratio. Then also, so if you look at the historical loss, we need somewhere around 5 to 6 billion, 7 billion cubic yard. What we did, we took the Morton's assumption and we projected into future the moderate scenario and left optimistic scenario, and we came with the accommodation space of 1.7 to 3.5, and then sediment need accordingly increased to 3 to 7. What I'm trying to project here is that this is the huge amount of sediment is there needed to offset this land loss, which is not possible, but we are trying to do as much as we can. So what are the sediment resources? One is the offshore sediment resources we have. Then the other is base and nearshore sediment resources. Then the sediment load which is going, as I said, going out to the river. Then the renewable sand deposit within the bed load within the river itself. Then you have the maintenance dredging sediment from which we get from the Army Corps of Engineers, they dredge every year. So these are the various sediment resources. So when you have restoration projects, different strategies, and the sediment is there, and we have different type of the sediment, what you need is sediment management. And that's where the sediment management plan of Louisiana comes in. So this is the sediment management plan of Louisiana, which we develop over a period of time. And I'm responsible for this development of this plan. And this has the 4 components. The heart of it is regional sediment management. And regional sediment management you do is really here. But how you do it is that you have to evaluate the sediment. When you try to evaluate the sediment, you need the sediment tools. And these are the tools, protocol exploration and that SOP and all these things that I will talk in a minute. And then you develop the borrow area, and the borrow area you manage and monitor, and then you have programmatic monitoring and adaptive management. Then the policy and regulation also comes in when you dredge anything. You put the first shovel in the ground and all the laws and regulation comes into play. And then very important thing is how you coordinate with the state and federal agencies and other stakeholders. So this is the different sediment management tool, Delta Sensors model of protocol for exploration. Then you have database, our database, and then you have the operational sediment budget, which I always recommend, especially for Barrier Islands. And then we have a tool we are developing that what is available and how we allocate the sediment. So this is one of the documents which I have developed and you can see on the website, this is general guidelines. And then we developed the SOP for our data management, the geoscientific data management. This is also on a guideline and our website. So this is our database, which has more than 2,000 data sets. Thousands of data is there, you can see. in that, and how the data are there, all the geoscientific data are there on that our website. With that, we developed this, and this is what I like to draw your attention, that you might, state of Alabama may think about. And also the LASARD I talked about, the state of Alabama contacted us, and they are developing that sort of database too. And this is the map, offshore map I'm proposing that we made for the northern Gulf of Mexico. This is the sediment distribution map, the first order. I mean, these are many things are we done. The green is the sand, and then yellow is the mixed sediment, and the red is fine, and some are unknowns. You can say lots are unknown here. So we developed this map also. But here is the rub. If you look at this, all this purple, guess what it is? It's all pipelines. And the pipeline is really what it hampers to the accessibility of the sediment. So that reduces a lot of the accessibility to the sediment. The availability is really much less than what happens, because you have to give the safety buffer of 2,000 feet both the sides. So that is there. Then we talked about what Army Corps of Engineers does. They dredge all this navigation channel, and they dredge about 80 million cubic yards per year. And all these things they use, but even after using that, this 25 million cubic yard is disposed of. And this 25 million cubic yard, ladies and gentlemen, can offset 1 year of land loss. So that is important that we use that, and we have proposed to how we use that. So what the future landscape looks like if we do nothing. This is what is predicted flood for the next 100 years. It goes all the way to Baton Rouge. You can see all this. Over 15 feet, 13 feet, 1 to 3 feet is the minimum here. So this is future look like if we don't do nothing. So doing nothing is not an option. This is, I borrowed it from Harry Roberts of LSU. So this is map of 2000. And if you look at this, we will lose some 10 to 13 square kilometers in the next 100 years, 21,000. And you see where the Baton Rouge will have, I will have the beachfront property there. So finally what it is a changing roles of the Mississippi River, from navigation, commerce, resource utilization, to flood protection, to now ecosystem. So how we balance that, that is the challenge. How we'll balance that, because that is important. That's the root cause. It is always said that the solution lies in the problem itself. So this is what it is. We have to go back to the river because there's renewable sources, and we have to do something about that. And how best we can do it, that will be our measure of success, really. And then the managing and restoring a degrading ecosystem is a complex and challenging, as I said, ladies and gentlemen, before. That's very challenging if you look into that. So for that, a planning is important, very important, and with complemented by adaptive management, because we don't have any boilerplate template for restoration of any of these thoughts. And how they will react, we don't know. So we keep on plugging on. And then as I said, and I will emphasize, the ecosystem restoration, ladies and gentlemen, cannot happen without sedimentological restoration. We have to pay attention to the gray below the green. The gray is much thicker than the green, the thin green on the top. That is what is important. And the sediment management is fundamental to the success of the large-scale sustainable coastal restoration efforts. And these are some reference over the only for sediment management. I'm just not making it up. I wrote in the peer-reviewed journal just to tell you. So that is all I have. I understand I take a long time that I say, but I get carried away and emotional when the sediment is concerned and sedimentary restoration is concerned. Thank you very much.